அழகா வேணும்பா. நம்ம ஹேண்ட் கிளாஸ் வைக்கணுமோ? தம்பி ஹேண்ட் கிளாஸ் வைக்கணுமோ? தம்பி ஹேண்ட் சொல்லி தாத்தா சொல்ல பார்க்குறாங்க.
Sir. Hello.
ஹலோ.
Screen is not clear, sir. Sir, screen is not clear, sir.
Should I share my screen?
Agastha madam. Agastha madam.
Sir? Sir?
Shall we start?
Yes, sir, you can start.
வாழ்க்கையெல்லாம் கல்விதானே வரமாகும். காமராஜ் கல்லூரியில் பொன் விழா கோலம். பொன் விழா ஓஹோ பொன்விழா பொன்விழா ஆண்டிலே ஆனந்தம் கொண்டாடும் நேரமே. கிரிகாராஜ் இடமே மதித்திட கல்வியில் உயர்ந்து நின்றோ. கல்லூரியே பூக்கள் சூழ கல்லூரியே பூக்கள் சூழ கல்லூரியே ஆடு மாணவியே. வாழ்க்கையெல்லாம் கல்விதானே வரமாகும். காமராஜ் கல்லூரியில் பொன் விழா கோலம். பொன் விழா ஓஹோ பொன் விழா. கர்ம வீரரை புகழ்ந்திடுவோம். ஏழைகள் வாழ எங்கள் வாழ்வில் கல்வியை கொடுத்தார். ஏழைகள் வாழ
ஏழையாய் இருந்தால்
எங்கள் வாழ்வில்
கல்வியை கொடுத்தார்.
யாக வாழ்க்கையற்றவர் நம் வாழ்வில் ஏற்றம் தந்தவர்
தியாகம் வாழ்வையேற்றவர் நம் வாழ்வில் ஏற்றம் தந்தவர்.
வாழ்க்கையெல்லாம் கல்விதானே வரமாகும்.
யா, யா, யா.
காமராஜ் கல்லூரியில் பொன் விழா கோலம்.
யா, யா, யா.
பொன் விழா
பொன் விழா,
ஓஹோ பொன் விழா
பொன் விழா.
பொன் விழா பொன் விழா ஆனந்தம் கொண்டாடும் நேரம் இது காமராஜ் கல்லூரியில் பெருவிழா
சந்தோஷ
பெருவிழா இது காமராஜ் கல்லூரியில் பெருவிழா
சந்தோஷ
பெருவிழா.
Thank you, sir, for the wonderful video about college. A very good morning to one and all connected. Let's start our desire for success, which is the first step for achieving greatness. It's a pleasure to welcome you all again in the final day of International Webinar Series on Intelligent Data Analytics. Let me first call upon the presence of our Lord Almighty to be with us throughout the session. A grand start of every function starts with a cheerful welcome. Now I invite Dr. S. Sendil, Associate Professor of Computer Science, Kamaraj College, Thoothukudi, to welcome the gathering. Welcome, sir.
Thank you, madam. Respected management of Kamaraj College, respected president of our college, respected secretary of our college, respected principal of our college, respected head of department of computer science and faculty members, and dear participants and my dear students, very good morning to all of you. It's my pleasure to welcome you all to the International Webinar Series on Intelligent Data Analytics Day 3. I feel immense pleasure to introduce and welcome our today's keynote speaker, Dr. A.S. Haja, Director, Data Science, Yardley, California, USA. Welcome, sir. On behalf of stakeholders of Kamaraj College, I extend a sincere welcome to you, sir. Now I welcome Dr. A.S. Haja to deliver his speech on the topic reinforcement learning.
Hello. Thank you, sir. Thank you for your heartfelt welcome. We're entering a new world. The technologies of machine learning are reaching a nexus of capability, which drives us to have artificially intelligent assistants to help us in every aspect of our lives. Deep learning with deep imagination is the roadmap of AI Springs and AI algorithms. Now, let us have the technical session on the recent machine learning technique called reinforcement learning with deep neural networks. Before starting the session, I would like to introduce today's resource speaker, Dr. A.S. Shaja. Dr. Shaja pursued his master's degree and PhD at Indian Institute of Technology, IIT Bombay. He has over 12 years of working experience across various corporate and research labs. He has a lot of experience in advanced machine learning techniques and have practically used it to solve several industrial problems. Right now, he is the Director, Data Science at InvestNet, Yardley, San Francisco, USA. He leads his team to do cutting-edge research and develop products. It's our privilege to have such a renowned resource speaker with us. I invite Dr. A.S. Shaja to share his practical knowledge on data science with us now. Welcome, sir.
Okay. Thank you everyone for the great welcome note. So, like in this presentation, I think like there are two things. One is a topic about like deep learning, and the other is a topic about like reinforcement learning. And in the final part of the session, like I will talk about how these two techniques combine together to take us to the practical world of the so-called artificial intelligence. Okay. I'm assuming like you guys are able to see me and things like that. But if not, let's fix that. Am I visible?
Yeah,
Yeah,
it's
yeah,
okay.
visible, audible.
Okay, sounds good. Great. So let me share my screen and start my presentation. So to start with, like I want to talk about like deep neural networks. And I spoke with a like organizing committee, and I got to understand that like there are different mix of people who are in this particular session. So my understanding is like there are some students, there are some research scholars, there are some faculty members, and there are some industrial people. So I will try to kind of make this presentation like more suitable for like most of the audience here. So there will be portions where it will be very useful for people who don't have much idea about all this, and there will be portions which will be a little advanced. So like as I go through the presentation, please note down your doubts, and I believe like there will be some time for us to discuss some questions towards the end, and we can like discuss all those aspects of it. So deep neural networks and reinforcement learning, these are like two important techniques that I've been like using on a day-to-day practice for solving like a lot of real life problems, mainly on the financial world, where my like company domain expertise like resides. So I will first talk about the basic intuitions for neural networks, because I have heard like whenever I speak to some people saying, hey, do you know about neural networks? They say it's a very complex topic, right? And then if I ask like reinforcement like learning, then like a lot of people are not even like probably aware of it. So I will spend first few minutes where we'll go with some basic ideas, because I believe that if you are good in understanding simple things, then trust me, very complex things becomes like extremely simple, right? So with that intuition, let's jump into the presentation. So I want to start by saying like what are the kind of like things that we want computers to solve, right? So the standard problem is it's kind of like a problem which is like pure structured text. So this is a problem where you're interested in predicting whether a particular user in a telecom company, like whether he will churn or not. So there are various features which captures like the amount of minutes that he talks, the amount of minutes that he spends in sending SMS, and whether he has like recently purchased anything in the last 30 days, and what is the data that he has consumed, his age. And we already know, say, some ground truth about like whether this user churns or not. And you are interested in coming up with a machine learning model which predicts whether this user will churn or not, right? Because if the user churns, then you can like go back with the user with some offer and try to retain the user. If you are like a Vodafone or whatever company, then you may be interested in using data science to solve such problems. Similarly, like you may be interested in taking a like a speech and then like convert into a language, or like you may want to develop an algorithm which identifies like music and portions like which are like top hits and things like that. Or you may be interested in like giving images or videos and interested in like labeling it as like motorcycles or not. And then you would be also say interested in like giving or developing algorithms which at the end of the day like gets converted into like self-driving cars, right? So we are at a world where all these things are possible, and we are, I mean, the last video where I'm talking about like self-driving cars is where I will take you towards the end of the session, where I will show you some demos of if you have to develop a self-learning car, what would be the code that you can write and simulate. And I will start from the basic problems, and towards the end of the presentation, you will understand. We would have like discussed all the concepts required to, even if you have to develop an algorithm for like say self-driving cars, right? So what it means is there is a lot to cover. So it's kind of like a very ambitious goal that I have, but I will try my best to take you through all these different phases and get you some basic intuitions and not bury you in like a lot of mathematical details, which I believe you can always refer. So that is the overall idea. So what are the kind of algorithms which can help to solve problems starting from a simple churn problem to an advanced problem like self-driving cars, okay? So first, I want to start with some pretty simple ideas. And I want you to like pay a lot of attention to this because again, I want to like repeat, if you understand some of these very simple ideas, trust me, you will become an expert in like deep learning and in learning like in no time. Okay. So let's take the simple problem of like identifying whether a user would like say churn or not. And let's take like two attributes, right? So for instance, let's assume say there are two attributes, which is say x1 and x2. For the time being, let us assume say x1 could be like say age, and let's assume say x2 in this case is the amount of time that the person is like talking. Okay. So let us assume say people who are older age, they may like say talk less, or say people who may like say teenagers, let's assume say they may talk more on a phone, right? So in this case, let's assume say the goal for us is say to distinguish or identify whether a user would say say is a like a teenager or a old person. Or we could also solve the problem, let's assume say people who are like talking more, let's assume say those are people, say in this minus, it's let's assume they are like people who don't churn, and positive here, those are people, let's assume say they churn, right? So if this is a kind of like problem, then the simplest algorithm that you start is by saying that something called as like linear regression, right? So basic idea here is like you draw a line, and the general intuition you hear is if you're able to draw a line which kind of like distinguishes the two classes, in this example, whether he will like churn or not, then all you're looking is if there is a particular point. So for instance, like for a given age and for a particular like amount of talk time, if the value is above the line, then you say that, like those people say churn. If the value is like below the line, then you kind of like say that those people say don't churn, right? So, I mean, it's pretty simple. All we are like trying to do here is linear regression, where you draw a line and you have like a sign function to say if the sign of that particular function is like positive, then you say the user like churns, and if it is like negative, the user like doesn't churn, right? So pretty simple, right? Now, the disadvantage of linear regression is overcome by logistic regression, where in addition to kind of like saying whether it is like just above or below, you also talk about the distance from the line, right? So basically you talk about how far a particular point is when compared to that particular line that is like distinguishing these two classes, right? So for example, if the plus sign is very far from the red line, then I can say with very high probability that, like this is a user who would not churn, right? Whereas if the plus sign or the negative sign is very near to the red line, then we can say that like I don't have much confidence. So my probability of whether this user will like churn or not is like very less, right? And there is a mathematical function called sigmoid function, which is a pretty simple function which tries to like capture it. I don't want to get into those details because this is not a lecture on like linear regression and logistic regression. But the basic intuition is if you have like a logistic regression, or basically a line which has the capability to also talk about the distance from, like where the line of separation is happening, then you can use that idea to call that as a probability. And that is the basic idea which goes into defining or like quantifying logistic regression, right? So I hope like the difference between linear and logistic regression is clear. And for this particular example, you would have like realized that logistic regression is more useful because in addition to telling whether this user would churn or not, it also gives the probability or the distance between that particular line of separation to distinguish these two classes, correct? So in this case, we agree and acknowledge that in this specific example, something like logistic regression is like more useful, right? And there are a lot of algorithms. And as I said, like this is not a quick recap of all the machine learning algorithms, but I just wanted to give you an intuitions, because if you understand the simple idea of like say logistic regression, then as I mentioned, I can like assure you that you will understand neural networks very efficiently, right? So why did I say that? Let us build on this. So let's assume say somebody said the point is like not about just like positives and negatives, which are just like linearly separable. But let's assume, say somebody said that the space is like this, right? For instance, the idea here is, let's assume X is like age, and X1 is like age, and X2 is like the talk time. Let's assume, say the middle, like working group or professionals, they are so busy, and let's assume, say they don't spend like too much time on, say, talking, whereas the left side and right side, which is, say, people who are, say, grandfather, grandmother, at the same time, like people who are like teenagers and kids, they spend a lot of time talking. So there is kind of like a middle portion where the behavior is very different when it comes to, say, distinguishing with like a talk time, right? So this is just kind of like trying to mimic that idea. And in this case, we are talking about like talk time and age. Yes, X1, I mean like X2 and X1, but for your problem of interest, it could be anything of interest to you, right? It could be height and weight, or it could be any variables. It could be like the length of the leaf that you're measuring, or it could be like completely anything which is completely based on the domain of interest to you. Now, the question here is, with the ideas that we have discussed in the previous slide, can I use logistic regression or linear regression to solve this problem, right? So the general impression that one may get is, no, I cannot have a logistic regression or a linear regression to solve this problem. But if you just like look at this very closely, then you will agree that we could just build on the same idea to solve it. For instance, you can have like one line which just focuses essentially on just like distinguishing the negatives and positives when it comes to this place, okay? And you can have another line in the top which distinguishes, say, the positive and like, like the negative in this particular space. And you can have like the third line which distinguishes the positive and negative in this third side, correct? So that makes sense. So essentially, using 3 logistic regressions or 3 linear regressions, I can solve this problem to classify pluses and negative, even though it doesn't look very trivially that like something like drawing lines could be like used here, correct? Now, this is the central idea which you are going to use and appreciate how a neural network will solve this problem. Because let's assume, say, there is a separate logistic regression or a linear regression. There is a separate function to talk about capturing this and this and this. What one could do is basically combine all of this. So what I'm just trying to say here is, let us assume, say, you are interpreting this particular point. So what it basically does is it tries to say the probability or the confidence that it has on interpreting, this particular point against all these 3 lines. So as an example, what this means is this negative sign, which is like circled in this green color, right? So if it is above this Z1 line, correct? So what I'm just like trying to highlight here is this particular line here, right? Are you guys able to see here? Like this line. So in this case, this negative symbol is above this particular line. So I'm giving a probability of 0.6 because I know it is like, it is not 50-50, it is like above it, right? Whereas if I take like the Z2 line, then when you take like this particular line, then this particular point is just below it. Make sense, right? So that's why I'm giving the value like 0.3. And if I take like Z3 line, which is essentially this line, so sorry, like I think Z2 is this, and the Z3, it's like very far, correct? So when I take this Z3 line, this particular point is very far from it. So I give a value like 0.8, right? Whereas Z2, it's like very near to it. So I'm giving like a value 0.3. So in this case, I'm just like creating a new problem or a new table, which is different from my original table, which was only in the form of like X1 and X2. Now I'm converting it into Z1, Z2, and Z3. And the moment I do this, it becomes like very easy to say that, like if the line is above the Z1 and below Z2 and below Z3, then it is like plus. And if it is like vice versa, then it is like minus, correct? So just like how a human would interpret these 3 lines to distinguish plus and minus, one could just make use of these probabilities to say if the probability of a point falling above the Z1 line is like very high, and the Z2 line is like etc., then you can very easily make a mission to understand how to like interpret this, right? Now, if I have to just represent this, then it kind of like becomes something like this. For people who know about neural networks, this is nothing but like neural networks, right? So what I'm essentially trying to say is like neural network is unfortunately not very complex. It is pretty simple. It's pretty easy to understand, provided if you like really understand the basics. So in this example, what we have like tried to do here is there was an original problem where we had like x and x2. We created like 3 lines and transformed that problem into something where the Z1 line just focuses on telling whether the point is above or below that particular line. Similarly, like the Z2 just does the same job and Z3 just does the same job, right? So we call that particular functionality of what Z1, Z2, and Z3 are doing. This we call it as like the hidden layers, and X1 and X2 we call it as like the input layer, and A in this case, whether it is a plus sign or a negative sign, we call it as like the output variable or the variable that we are like interested in like observing, right? So this is essentially the central idea which actually revolves around the entire neural network world. And I would like to show you a quick practical demo of how this is like used in practice, right? So if you take like this particular example, so you can just go to the site playground.tensorflow.org, or just like search for like TensorFlow, which is a powerful library, which is just like lying behind this. So in this case, like there are different type of images which are there. And this is just to give you a practical intuition of like what is happening, right? So in this case, if I tell just like 3 hidden layers and the 2 output variables where I wanted to kind of like distinguish the 2 points which are like orange and blue, then if I just like run this simulation, this is like over multiple iterations. What the algorithm is like trying to do here is it is trying to basically identify the values of the different like Z1, Z2, Z3 kind of like lines. Actually, what is happening is if you look at this particular like neuron that I'm like kind of like trying to highlight here, if you look at the shape of it, right? So it's just focusing on just like finding out or distinguishing this shape, right? This particular neuron is just like interested in distinguishing this shape, and this particular neuron is just interested in distinguishing this shape. And interestingly, when you just build one more layer on top of that, using this as the building blocks, then you are like surprisingly able to find out that using this architecture, you are able to like kind of like identify that there are 2 different classes of objects which exist, correct? So you could take, like multiple different shapes, and I spoke about like a logistic regression, which is like explained through sigmoid. There are different type of like activation functions you could play with this. You could add more neurons, you could add like less neurons, you could add more variables, and you could like play around and do some simulations to see, like how good like this problem is being solved through neural networks. But the whole point which I wanted to like emphasize here is, if you understand this intuition of, okay, whatever comes to input is just the raw form, and there are like these hidden layers, which just does a very simple job, right? It doesn't solve the whole problem. It just focuses on, distinguishing whether it's a straight line or a vertical line or a slanting line or this. And then there is like higher order outputs or like higher order like hidden variables. You can have like more hidden layers and things like that. And what the algorithm will do is just uses the building blocks as the basis and essentially, like try to solve a problem which is like, like very complex to solve like otherwise, right? So this is the whole crux of the world of like neural networks. And, it is like very powerful, right? Because it's kind of like something that if I give you like a problem like this, and tell you to develop an algorithm to say distinguish anything, if you take like any algorithm, you take logistic regression or a standard algorithm, by itself is going to suffer a lot. But the idea of neural network where you have this hidden layers, which just focuses on doing like a specific set of things and then using that as the building block to achieve a higher goal is like, something which is pretty awesome. And that is the bread and butter of how the neural networks like operate, right? So now if I have to like change gears and talk about solving like real problems and try to highlight why neural network is like so famous and popular now as opposed to like like quite some time back, because this is not an algorithm which got created before 10 years or something, right? This is an algorithm which has been there more than 30 years. But the reason it got like famous is something like that I will discuss in the next few slides. But I hope you got a basic intuition of understanding and interpreting neural networks. So let's get into some details on why deep learning now and why it was not famous like before, right? If you take like a problem of like kind of like unstructured text, structured text, like the one that we discussed here, right? Where you have like a tabular form of data, which is like the most common form of like data which is used for solving like machine learning problems, then that is like kind of like, beaten to death in terms of like wide variety of algorithms that we have like discussed here. So neural network is useful, but it is not necessarily required to kind of like solve that kind of like problems. The actual problem comes when you deal with something like this, right? So what we see here is like an image of a bike, and what the actual computer or the camera sees is a set of like values, right? So which is like the RGB values of each and every pixel. So what this one is trying to say here is if you take a small portion, say 12 by 12 or something like that, then those are the values which are like in this particular pixel, right? And if you apply some standard algorithms like random forest or linear regression or SVMs or anything like that, the first problem that you need to solve is come up with the idea called feature engineering, which means what you have to do is like if you just give the pixels as such as a pixel 1 as the first column and the pixel 2 as the second column and so on and so forth, and if you develop a training set by saying whether it is a bike or not, then as you can imagine, it's not going to solve, right? Because some bikes can be, like scaled differently. There could be a bike which could be standing in opposite direction. So if you assume that the steering has to come this side, then it cannot be, detecting bikes where the steering is in this side. So there could be like a bike and car. If you're just looking at understanding some wheels, there could be a car which could also have like wheels. So there is like, just by using pixels, you cannot like solve this problem. So in other words, if you just like look back several years back, then the standard machine learning algorithms were not able to solve problems which was not captured in a structured form, right? So what people did at that time to solve this problem is they came up with features which would identify edges, wheels, handlebars. So for instance, let's assume I have written an algorithm which builds on top of like edge detection and identifies, okay, if the edges are smooth and something like that, then it is a circle, right? So let's assume I call it as an algorithm for identifying wheels. Let's assume, say, I have developed a similar algorithm for identifying like handlebars based on, like whether it is straight and some angles and stuff like that. Then I encode another feature. So basically what you do is you take a original raw image, you develop some features on top of those raw images to identify circles or, like handlebars and things like that. And then you use the standard workhorse of machine learning like SVM or whatnot, and then try to like solve the problem of like whether it is a bike or not, right? But as you can imagine, like your energy will be like entirely spent in just creating those features. And today, if you are detecting bikes, then you have to create features. Tomorrow, if you have to detect faces, then you have to detect features related to how an eye will look like, what is the distance, between like your eye and nose, or whatever. There are like whole lot of feature engineering that is like required, right? But the beauty that neural networks brings it to the table is just similar to the whole idea that we discussed previously, which is you just give like the original raw pixels, and the first layer just detects some different angles of lines. And as you can imagine, like these angles of lines, basically using small set of lines and curves, you can create like more complex shapes like eyes, nose, and things like that. And using those complex shapes, which is a hidden layer, you can create like the entire shape, right? So that's what basically neural network does. And this is just a simple pseudo architecture to capture this idea of like, what really happens, where the input is, if it is 25 by 25 pixel, the input 1 is like pixel 1, pixel 2, what is the RGB value at pixel 1, pixel 2, etc. And the layer 1, it is basically logistic regression, which just detects this kind of line or whatever kind of like shapes. And then the higher layers builds on top of that to develop like more complex shapes. And the further higher layers or the output layers of interest to distinguish whether it's a shape of a like the name of a person who is like say Shaja or say Dr. Joseph Raj or anything like that is something that is built on top of this, right? So this is the beauty of neural network. And the main essence which I wanted to kind of like argue here is, as opposed to the problem of how we solved the problem earlier, where you take the image and you have to do feature engineering. You have to write an algorithm for detecting edges. You have to write an algorithm which captures, whether there are like circles in it and things like that, where basically you take an image and convert it to a tabular form. In the world of like neural network, there is no feature engineering, right? So if you have like experience developing machine learning algorithms, you will realize that the time is not spent on actually running the machine learning algorithm, right? The actual time is essentially spent on feature engineering, which is, let me try this for, I'm solving a churn problem. Let me try, if I create a variable which captures like year-over-year growth, whether it is helping or not. If I include a variable which says, whether there has been recent increase, whether it is helping or not, right? If I include a variable of country, whether it is helping or not. If I include a variable, the age of the person, whether it is helping or not. But welcome to the world of neural networks, where it says you don't have to do anything like that, right? All you have to give is just give me the input, just give me the output, and I will take care of doing this feature engineering all by myself through this beauty of this hidden layers, wherein you are able to like kind of like solve this problem, right? So this essentially is a very powerful idea, which I wanted to kind of like first talk about. And if you have these intuitions for it, then you can go back and understand any kind of like neural network architecture. And the reason why this is like getting famous now, and why it was not like famous before, was because of the computations and the cheap, like technological infrastructure which is available now. And this is a simple example again to kind of like classify faces and cars and elephants and chairs, where the essential idea is just the same thing that we are like discussed in the previous slide. And just to emphasize, if you have ever wondered, hey, why is neural network or why is like deep learning famous now as opposed to say 30 years back, then I want you to go back with two things. One is the feature engineering is the most difficult and time consuming exercise, and deep learning kind of like completely gives you a freedom from that, right? So this is like the first reason. The second reason is, even though deep learning is an algorithm which was like developed before several years, we didn't have the necessary cheap computing resources to solve all these complex, like changing. So what I'm just trying to say here is like, for you to kind of like try all these things, you need to be like doing some computations to determine the specific numbers that I had like initially discussed on the triangle shape problem, whether it is 0.6, 0.3, all those numbers in the regression has to like get inside, right? So to do this for all the pixels and stuff like that, it takes like an enormous amount of time in before 30 years. But now it takes like 5 minutes, 10 minutes. And I will show you guys like some demo towards the end of this to give you that intuition on how this is like used to solve like real world problems, right? And the last point about like deep learning is why it is getting famous is, if you look at like the general machine learning algorithms, like linear logistic regressions and SVMs and random forests and things like that, then if you give more data to it, but there is a particular point beyond which the machine learning algorithms will like kind of like saturate, right? Whereas if you look at like deep learning, then these are algorithms, if you give like more data, then it's going to perform like much better. So as you can imagine, we are living in a data world where the data is not like scarce, right? It's like a lot of data is available. So that is like another third final reason that I wanted to kind of like you to go back with, which is helping like the deep learning world to become like a lot more famous. And the final conclusion that I wanted to give before I change gears to talking about like reinforcement learning, which is a very beautiful formulation, is we are living in a world where when I look back the research literature, and if I ask a question, what is the best algorithm for detecting faces, right? Then somebody would have like developed an algorithm using some rotational features or some complex transformations as features and called that algorithm as the best algorithm for detecting faces, right? So separate feature engineering for faces, and he has like an algorithm which does only face recognition, right? And if I were to ask a question, okay, what is the best algorithm for detecting, say, speech? Whenever I'm speaking, like let's assume the computer has to understand it, and let's assume it has to do some translation. Then there would be a separate feature engineering part of speech tagging, etc., etc. And the separate feature engineering specific for that language, it would be tagged as the best algorithm for translating, say, English to, say, Tamil, right? If I ask the same question across any other kind of problem where, say, if I'm smiling or laughing or crying, if I have to like detect my emotion or sentiment or anything given an image, then there will be a separate algorithm, feature engineering, based on what do you mean by like smile, all those things. So, but interestingly, if I look at today, it is the same algorithm which is which has like bet all the other algorithms. So the best algorithm today to detect faces is not that same algorithm which was developed by somebody based on feature engineering, but the simple answer is deep learning. The best algorithm available today to do machine translation is again deep learning. The best algorithm to kind of like detect whether I'm like smiling or crying or anything today is again like deep learning, right? So gone are those days where there is a need for a sophisticated separate algorithm to solve that particular problem and spend your lifetime doing feature engineering. There are people who develop such algorithms. Their entire 25 years of like research and their career goes into just feature engineering, right? And all those has been like beaten now just with this simple common algorithm called like deep learning because of the ideas that we like discussed, right? So I want you to go back with this motivation that deep learning is very powerful, but at the same time, it's pretty simple if you understand it right. And as I specifically didn't want to get into the mathematical jargons, given the wide variety of like interesting set of people who are here. But I hope like you got the intuition of why deep learning is powerful, why it works, and why like the world is like moving towards in that direction. Okay. So with that, let me now change gears and go to talk about reinforcement learning. I could talk about like deep learning for like more than 10 hours, but I'm kind of like cautious about like my time limit here. So I'm changing gears to talking about like something called reinforcement learning. So the interesting insight about deep learning is it's kind of like the killer algorithm for solving like most of the problems, right? But if you have to like take a simple example, so this is a game of like ping pong. So let's assume say the green is the computer and say 7 is a standard player, right? So with this understanding of deep learning that you have, if you have to develop a game of ping pong, let's assume you are a data scientist or a developer who is like trying to solve this particular problem, then how would you go about solving this problem, right? So you will go back to the standard world of supervised machine learning, where what you would do is you give this image one, and you would have like recorded what an expert player. Let's assume the green was initially an expert player, right? So you would have observed what that expert player in the sense. Let's assume for the time being the orange was a player who lost, and the green was a player who won, right? Now, what you would do with a deep learning based idea or machine learning based idea is you will take a particular set of images and say, if the game is in this particular position, right? The expert player moved the like handle from down to up, right? So you will say up. So you will say the input pixels, etc. Say separate different columns and stuff like that, and then you will have a final like ground truth based on what that expert player played, whether you would say whether it is up or down. Are you able to like visualize this problem, right? So if you visualize this in the form of like a deep learning based architecture, so what it would mean is the input layer is like pixels. So as an example, let us assume say the image or like the board, the resolution is like 25 by 25. or let's just take a simple resolution of say 10 by 10. Then there are 100 input layers, correct? There are 100 neurons as the input layers. And then you are essentially the output layer is what that expert player did if the input was in a particular form, correct? So if the expert player like moved the bat up, then you are expecting the machine to learn that the bat has to go up. If the image is in a different shape where the ball was in a different place, and if the expert player moved from like up to down, then kind of like tell the machine the ground truth variable saying like the machine has to like now move the handle from up to down, right? So I hope like this basic idea is clear, and using some hidden layers and all those things, it understands this image better. So it basically translates a given image. Whenever it sees a particular ball and a particular handle of the opponent player in a particular place, just based on how an expert player did, the machine has like now learned using a neural network architecture how to move the position of these bats, correct? But is this good enough? Maybe. But how do you now beat a human, right? Because at max, what I can do is mimic an expert player. But if I'm playing against the expert player, then it will be like kind of like a situation where at max I can beat him. I mean, at max I can like draw him because I cannot go beyond him, because at max what I have learned is similar to the behavior of an expert player, right? So that is a limitation of standard supervised machine learning. And the second limitation of standard supervised machine learning is if I have to solve a problem using like standard deep learning or using these ideas that we've already discussed, then as you can imagine, it's kind of like you have to generate like multiple snapshots, right? Of, okay, if the picture is like this, take a print screen and convert it into pixels and say whether it is like up or down based on how the expert player moved. You have to basically generate a millions of moves for you to like develop an algorithm which can be used to solve a problem of ping pong, which is a simple game as in this example. So generating this training data and this ground truth is a humongous task if you are going down the path of like doing this. Fortunately or unfortunately, this is how a lot of machine learning based algorithms related to playing games have been like developed. So they make a lot of expert players to play and like use that as the basis. So they will have like different levels. So when you say the game level is like easy, they would invoke a machine learning algorithm which was developed playing against an easy player. And if you say medium, then they have training set based on a medium player. And you say like it's expert, they would actually show you the machine learning algorithm that they have developed on top of like the expert player, right? But at the end of the day, the machine is not able to beat an expert because at max what it has learned is an expert. But if I look at literature, then there are examples like AlphaGo, which is kind of like a game. I don't want to get into the rules of this game. Like you can like probably read it, but it's a game where there is like championship, which happens like on a periodic basis. And in 2017, an algorithm which is based on reinforcement learning, it kind of like bet the expert player, right? So how is that possible? So that is the basic idea that we are going to discuss here. So the general idea is, it's a very interesting formulation because it mimics like the real world where if you are the player, if you are the person who is like developing that algorithm, then you call that person as like, as like agent, right? So my algorithm is like agent. And instead of telling the right move is up or down, what I actually get to see is some reward, right? Which is in this case, just the points. So if I move my bat up and if I'm able to like gain a score, then I get a positive reward. But let's assume say I moved it up and then I kind of like lost a point in this game of like ping pong, then I get a negative reward, right? And then environment is just a copy of like the picture of the image. So the main distinction when compared to the supervised machine learning algorithm or through deep learning that we have like discussed is instead of you telling the algorithm where the final output variable of interest in your deep learning architecture is like up or down, just based on the ground truth that you have generated, correct? In this case, what you are telling is you don't tell the machine to do up or down, but rather it just like randomly tries things and you give a reward, which is nothing but the scoreboard, right? If it sees the scoreboard is like increasing, then it treats it as a positive reward. and will try to do those kind of moves. If it is like kind of like reducing, then it will kind of like feel that it is a move that I like, should not play, and it would minimize such kind of like moves. And this process like repeats. So eventually what happens is it will discard all those moves where it lost points, and it will try to reuse all those moves, complex moves that is like initially tried randomly. It will kind of like try to do again and again and again, where it gets, if it gets like positive rewards again and again, it will try to do all those moves again and again. And we'll come to a phase where it can beat an expert player, because it just focuses on rewards as opposed to mimicking or learning from a ground truth which is generated from a standard, say, a standard expert player, right? So just to give you like some technical details into this, what we're essentially talking about is like if I move from up to down, etc., etc. Let's assume say I win, and if I do like some other moves, I lose. And so what it basically does is the probability of making similar kind of moves. If it was up, then I go down, and if it was up, then I again like go up. It will try to do all these moves which I'm like winning in a probabilistically increasing more way down the line, and minimizing these moves which have actually like made me to lose, essentially becoming or developing or getting into a shape where it becomes an algorithm which becomes like extremely powerful, where a lot of times you would be just making moves with just like wins. And that is the example that we saw with like AlphaGo. Out of like 3 out of 3 games with the world champion, like this algorithm which was developed by like running behind the scenes for 21 days, it was like able to just like beat it. And today the same algorithm could like probably run in a fraction of days, because of the ever increasing advancement in the computing infrastructure, right? So to give you a little more color in terms of how this is like actually done, there are some jargons, and I mean those jargons and the technical details, I mean definitely we don't have like time to discuss it, but I will give you an intuition so that if the concepts are clear, you can like refer, and if you have any doubts on some of the mathematical formulations, feel free to get in touch with me. So the basic thing that we are dealing here is, if I take a simple example of solving a maze, right, where there is a dinosaur, let's assume say that is you, and these are so the first word that I want you to remember in the world of reinforcement learning is something called as agent, okay? And this is a reinforcement learning agent, and the reinforcement learning agent, the second terminology I want you to learn is something called action, okay? So it can make actions. So in this case, if you're thinking about solving this maze, then it can make actions like go up, down, right, left, right? And then it gets like rewards. So for instance, like if it kind of like got into a bottleneck here, then it will get a negative reward. So it will not try to go here, because it already knew that if I go, like up, down, say up, down, then it knows that the reward is going to be negative. It will minimize that moves. And it will kind of like try to find a way where it was able to increase its like reward continuously, and eventually like get to the final portion, right? And the state represents how the environment changes, in the sense the position of the like small dinosaur at like different stages. So if it was like after 3 time steps, so the dinosaur could be here, and the state would just reflect the state of that particular board at that time, right? If you're thinking about this as a chess game, then this could be different moves that I make, and this could be rewards related to, you can like assign, I mean, you can say if you just like kill the king, then it is like an infinite reward, but if you kill like other pieces, you can give like better rewards. And there is a concept of trying to reach long-term rewards, right? So there are algorithms like dynamic programming and deep learning that I will like quickly touch upon, which helps you to essentially achieve that. So what I'm just trying to say here is, if you take a game of chess, then the algorithm like will focus on attaining this long-term reward and not on the short-term reward, right? So for instance, like you may kill like the opponent's like pawn or something, and you may get like a reward of just 1, but the next move he should not like come back and kill your like bishop or anything like that, right? Because then in this case, it's a short-term reward that you're getting, but in the long term, your reward is like going back. So the algorithm doesn't just look into only the next move, but it kind of like, since it's a computing machine which can like forecast and try the probability of rewards in a long-term basis. It will look at all the long-term possibilities, find out that one which gives the longest reward, and then tries to like take that. And this process repeats, and eventually it learns all those strategies which gives the best rewards. And that is what defines that agent. So it will just try to redo all these things on a continuing basis. The first time there is some learning exercise, but after that it becomes essentially a powerful algorithm which can beat like humans, right? And this is the same idea which is just used not for like solving games, but it is also used for trading in the stock market these days. I'll show you a demo. And also for, if you know the world of like self-driving cars, then it is virtually impossible to generate billions and trillions of images and say the car to be taken like right or left or press acceleration or anything like that. It's kind of like very difficult. So what people do is they generate kind of like a map and generate a reward. If it meets an accident, then they give like a very negative reward. It kind of like goes and follows the rules. And if it was able to continue, then kind of like the reward increases. This process is repeated. And that is the algorithm which goes into like kind of like self-driving cars and things like that, right? So just to give you like some more color in terms of understanding this, sometimes like the rewards are more complex than a game like ping pong. Because in a game like ping pong, I mean, you can like get a point or not just based on what happens very quickly, right? So every time you just like win, then it's a strategy that it can kind of like try to like redo again and again. But if you take like a game like this, the end goal is for a player here to reach here, right? So again, the moves are either go up, right, left, down, jump, etc. And if I have to like just track all these moves, then it's kind of like very difficult. So you can give some short-term rewards. For instance, if this player, if it was able to overcome the skull in this example, right? So you can give some reward. Or if you're able to like kind of like persist in this game for more time, that can give like more reward. So it is not always the reward is just like focused only on that, but also the rewards can be sparsely given, that the algorithm like kind of like learns and tries to overcome all these like disadvantages, right? And the last bit of terminology is here, if you're interested. So this is an example of like a maze problem, and here is like your agent. So there are two more things which are important to understand. So we spoke about some three terminologies, right? One is the concept of agent, and then it takes an action. Agent is similar to your brain or your algorithm. It takes an action and it gets rewards. We spoke about like these three terminologies, and the environment, it provides you an observation. So which is basically the change in the board or change in the scene. If you're like talking about a self-driving car, or if you're talking about like like stock trading, then how much money you made because of your investment on say Google and Apple and IBM or whatever it is, right? So that is like the environmental observations, and you kind of try to do all these things. Two more terminologies, if you're very interested in reinforcement learning, that you need to be aware of is an idea called as policy and an idea called as like value function. So the middle picture is a representation of this idea of policy, and the last picture is an idea of like value function. The idea of policy here is, given a particular state, then in this case, the policy is just nothing but the behavior of the agent, right? So what this policy says is, if I'm in this particular block, then always go up, right? Because if I go down, then I'm going to kind of like get a deadlock, right? So if I'm in this particular place, always go right. And here again, like go always right. It's just like the behavior of that agent is captured using this idea of like policy. And the value function is, like the overall long-term reward, right? So for instance, if I reach the goal, then the penalty is -1. If I am just before that, the penalty is like -2, etc., etc. So if you let the algorithm to generate this matrix one time, then it is easy for, if you just like generate all these values one time, then the next time it has to like solve it, it is pretty easy, right? Because you have to just go through the value functions in the decreasing order. So for instance, when it is here, it will go here because the value function is like decreasing further. So it won't go in this direction because it has already learned. Now it will go in this direction. It will continue to go here, in such a way that like it reaches the value function, which is like finally like minimized, right? So there are algorithms which are designed to minimize the value functions or the policies. So there are kind of like this two kind of different algorithms, which is focusing on like policies as well as like value functions. So essentially what it means here when it comes to applying deep learning for a reinforcement kind of like setting is, if you think of like this as kind of like a problem where there are like blocks which are falling down and you have to like kind of beat it, or if you have to like kind of, this might be a game which might be like familiar with, where you have to like beat all these blocks which are in the top. So what happens here is there's a set of like neural networks which are created, and the final thing that you are doing here is basically the moves, whether you should move your joystick towards the right 45 degree or just like 90 degree, like negative 45 degree or whatever it is. And based on the points it gets, which is like the rewards which gets into it, the algorithm kind of like learns again and again, and it learns those strategies or policies or value functions which are like optimized, and the algorithm will learn and remember that and will continue to do that in future so that it becomes like better and better, right? And this again is a kind of like a simple formulation where you have a kind of like a game, and you have like a deep learning, and you have like the different type of arrows which are here to define whether you should go up or down or etc. And what the algorithm is learning is finding all those combinatorial moves, which kind of like helps to maximize the probability of like winning, and the algorithm will like kind of like remember that to win, right? So I know we are towards the end of the session, but I have just like a couple of more slides. So the first thing which I want to show you here is basically an example of how reinforcement learning is used to stock trading, right? So the idea here is, let's assume, say in this simple example, so you have gathered some 5 years of data, right? And you have like 16 stocks from NASDAQ, say Apple to Dish and eBay to Facebook and Google and whatnot, right? And the idea here is like you are given, let's assume, say $1 million, and instead of watching the news and changing my positions on whether I should invest on Apple or Costco or eBay or Facebook or Google, you are letting the algorithm to learn based on whether it's losing money or things like that. And you wanted to basically use reinforcement learning as the algorithm to beat a particular human, right? So the whole idea here is, if you develop an algorithm, what it basically does. So if I had to like ask you what would be kind of like the objective here, the objective here is, like maximize the portfolio value, right? Basically, if I'm making more money by, putting money on a particular type of like stocks, then I'm interested in like maximizing the overall money. And the environment is the particular returns of the portfolio at a given point in time. So for instance, today, let's assume I have $1 million or say 10 lakh rupees. And if I spend 25% of it in Apple and 50% in IBM, etc., I might get say a return of say 10%. Say my 10 lakh might become like 10 lakh and say 1 lakh or say 11 lakh, etc. Right? But if I allocate it in a different way, then I may get like 12 lakh or maybe like 5 lakh, or I may be like moneyless. So that is the reflection of the environment. And the states is I could like the portfolios, I could like kind of like invest more or like less. I could like put money into it or like take money from it, and those are the different actions that I can take. And the reward is whenever my money is like increasing on a given day or after a particular time stamp, then I'm getting like a positive reward. So whenever it is like becoming like negative, then I'm kind of like getting a negative reward, right? Now, this is a piece of Python code where the whole idea of just these rewards and things like that are just like coded here. I mean, I don't want to get into just the coding parts of this, but the idea is like essentially the same, where you specify all these parameters and then you let a deep learning algorithm just to like kind of like learn, and you kind of like train it. And after it trains, so this is done using like SageMaker, which is an environment which is provided by Amazon Web Services, where the libraries are already installed. So if you are a geek person who wants to install everything on your own, then this is like probably not required. You could just run it on your local machine. But in this case, I wanted to just reuse all those libraries which are already installed and save my time on installation. So that's why this demo is shown in this browser here. So what I wanted to kind of like highlight here is, as you can imagine, in the initial phases, right, the algorithm is not able to make money. it's kind of like losing a little bit, and eventually it picks up, and essentially comes to a point where it's like reaching like a lot of money, right? And this is again like kind of like different type of simulations, which is like showing that you could like make money if you just build on this particular idea of using reinforcement learning to solve this kind of like problems. And this is a particular problem for the self-driving car. So in this case, yeah, I think it might be a little overkill, but I will see what I can do here. Okay, so it looks like I may have to like just run this, and I thought I had like already run it. It might take some time, so I'm like sorry for that. But you know, maybe like we can come back to this after the Q&A, and I'll be able to show you if you have to like develop a self-driving car. This is a algorithm that basically just uses reinforcement learning, where if it gets out of the track, you give like negative points, and if it just continues on the track, you give like positive points, as opposed to telling algorithm take right or left. The algorithm learns on its own how much speed it should go, whether it should take right or wrong, just based on just the whole idea of like rewards, which is like coded here. So I'll try to come back to this after the Q&A part. But overall, in terms of like what I wanted to talk about, I think the idea of reinforcement learning is a very powerful formulation. And the beauty is it is similar to how we learn, right? If you take an animal or if you take a kid, how they learn is by trial and error. So for instance, if I touch fire, if it hurts, then I won't touch it again, right? If I fall down, if I'm running on a particular speed, if I fall down, then I won't do it again. The same behavior, the nature is teaching us, and nature is very powerful. And this is probably the first time people are thinking about using that to kind of like formulate things, right? So that becomes like extremely powerful, as opposed to telling what is right and wrong in a very computer-based way. We are trying to model a framework which is very closer to mimicking nature, by giving rewards when you do right things, and punishing or by giving negative rewards when you are making mistakes. And the deep learning is a very powerful computational framework. You give like input output and say, this is what I am giving you as input, and this is what I'm giving you as output. No feature engineering, but it does all these experiments and kind of like comes up with an algorithm and strategy to maximize the overall objective. So according to me, the real AI is very near. And that can happen by combining reinforcement learning, which is the problem formulation, and deep learning, which is the problem solution. So this is a problem and solution which can solve real AI. So that's all I have. I guess like I probably went a little more time than I probably 5 minutes beyond the time which I wanted to take. But I hope like that was okay. So let me stop here, and probably we can take some questions. And if by the time, if my self-driving car code completed, then I'll be able to show you that as well.
Thank you, sir. Thank you, Dr. A.S. Shaja, for your mind-blowing technical presentation with practical examples. I know you are spending your night time. That is, I think, 11:30, around 11:30 at here in USA now. You are spending that time with us. Thank you. Thanks a lot. I think your deep lecture reinforced the neurons of our brain to work effectively on deep neural networks. Thank you. Now the time for query session. The participants can unmute themselves and ask their clarifications. Whoever is supposed to speak.
Hello, sir.
Hello.
Sir, myself Praveen Suramani. I'm an assistant professor, and I'm doing part-time research in deep neural network, actually convolution neural network. So I have some doubts. I need some clarification, sir. Sir, in convolution, in reinforcement learning, there is some sort of convolution process, right?
Yeah, it depends. So the general idea of convolutions is, the whole idea is about, like if I have to give you an example. So I may be having a phone, I may take a picture from here, Or I may take a picture very nearby, or I may take a picture here, right? I can take a picture of a bike very far, very near. So different scales, right? If I look at like feature engineering just based on just a particular frame, which is like a 25 by 25 pixel, then what happens is when the different images are in different scales, the learning collapses. When I say collapses, if I have like learned based on an assumption that the bike will be typically in this entire frame, but finally when the bike was like in a scaled down version where the picture was very small, then convolution, I mean like the entire simplistic form of MLP or multi-layer perceptron breaks, right? Because it was expecting the pixels to be in that particular order. But convolutions helps you to model that higher order features wherein you are collapsing a bunch of pixels and treating that as a kind of like a feature. And then you are collapsing a larger set of pixels. For instance, your first layer of convolution could be 5 by 5, where you are collapsing 5 pixels at a time. And second layer of convolutions could be 15 by 15 pixels at a time. So you get to give an algorithm a chance of looking at different scales, and that's the power of convolution. Now, whether it is useful for reinforcement learning completely depends on the type of problem you're solving. If your problem requires the input to be available in different scales, where, for instance, if you're talking about a game of, say, playing soccer or cricket, where if the ball comes near, then the size is bigger as opposed to the ball which is like far, then probably convolutions are definitely required for such type of like reinforcement problems. Whereas if you're solving a problem like ping pong, it kind of like is useful, but it is not very useful as opposed to some problems where the scale of the entity of interest kind of like changes, right? So it kind of like varies, but it is like a powerful technique which is used to reduce the dimensions and to play with the different scale which happens in the neural network world.
Hello, sir. Hello, sir.
Yeah, right.
Sir, I am a research scholar doing medical image diagnosis using deep learning. However, the problem which I am facing is that the panel is asking, how are you sure? Because it is a black box. How can you prove that it is indeed doing the work? So can you just let me know how I can say that this deep learning indeed works?
Yeah, so it's a good question and it's a tricky question because at the end of the day, the power of an algorithm lies in the details, right? People say the devil, I mean, yeah. So in your example, what I can tell you is if you just like look back and look at the general research literature in terms of what kind of algorithms have solved similar type of problems, people have benchmarked. A lot of researchers have said that the same data set, if you use deep learning as opposed to other algorithms, then they have shown, I can point you to some specific references, and they have shown that for all these type of problems, deep learning is the winner, right? So, at this point in time, what we have is evidence, which is done by a lot of researchers working on similar problems, showing that deep learning could solve such type of problems. And the world is going very innovatively in using deep learning and self reinforcement learnings to solve a wide variety of problems. So for instance, like I have a friend of mine who has a startup. What it does is whenever you open your fridge and takes an item, right, it does like automatically identify what you took in spite of wherever you kept, whether you took a chocolate or whether you took a drink or anything else, it just identifies it. So whenever the refrigerator goes on low stock on a particular item, it just sends you a message to refill it. Or if you're going to a shop, it just like does the automatic billing. There's no need for a biller, right? So all these are just done by using like the ideas of like deep learning. And if you look at it, it's all just images, videos, where all these things which previously people are not able to think of doing feature engineering to play with, deep learning has been able to solve it. So what I gave is a very simple practical example that I know, but if I'm in your position, I would definitely give a try by using, because in this world of data, the details are actually in the data. Unless you try it, you really have no idea. And given the infrastructure of all these deep learning frameworks, which are available in AWS or Google Colab or anything like that, which are very cheaply available, I would strongly recommend you to just give a try. And if you face any hiccups, then definitely you can reach out and I can give you whatever guidance that I think based on my experience is useful.
Thank you, sir.
Sure.
Good morning, sir. Good morning.
Hello.
Hello. Good morning, sir.
Hi. Yeah.
Can you hear me?
Yeah. Please go ahead.
My name is Dr. Anil from
Okay.
Kerala. Okay. My name is Dr. Anil.
Yeah, sure. Hi.
Kerala.
Sure. I'm able to hear you. Please, Dr. Anil, go ahead.
Yes, sir. The presentation is very good and nice, sir.
Thank you.
Very good and nice. That is my feedback. Good presentation. Very good. Thank you
so much.
Thank you for the presentation. Okay.
Yeah, you're welcome.
Okay.
So this is Renosha.
Yeah, hi. Yeah, I'm able to hear you. Please go ahead.
Good afternoon, sir. This is Rajeshri Shedge from Nerul, Navi Mumbai. Sir, is there any limit on the number of hidden layers that we have to call a neural network as a deep neural network? Any limit on minimum number of hidden layers that we should have under deep neural network?
That's a good question. So for that, I would like to share my screen again and walk you through a simple example to illustrate this idea, right? Are you guys able to see my screen? Yeah. So
yes,
if I take like this particular problem, right, where there are only kind of like two different type of things, right? There is no need of 4 neurons because at the end of the day, if I could just like do a straight line, right, then that will just do the job by itself, right? Whereas when there is a more complex shape, then there is like need for more neurons, correct? So what I'm just trying to say here is, in this simple example, if I create like several neurons, then those are useless because, like it is just an overkill. There is like no need for them to have like any role to play, right? So similarly for your problem of interest, if you realize that, like if you have some domain knowledge saying, okay, I think these are the kind of features that I would think of. So you may want to start with that many number of neurons as your hidden layer. That is a good starting point. To specifically answer your question, is there a limit on the number of neurons? I don't think like there is a specific limit per se, but there is a problem called as diminishing gradients. As I mentioned, I mean, I specifically didn't want to get into a lot of mathematical jargons, but what it just does is, if there is an algorithm called like backpropagation. It just basically tracks, the differentiation across like the entire chain rule in a very optimized way. So when the gradients goes for, very small value, and when it have to like divide by a very small number, then it kind of like just like explodes. Just because it is doing something useless, it will corrupt everything and will, change a lot of values in a disrupted way. So I would not recommend like so many doing experiments with like, simple smaller hidden layers, measuring the performance and then increasing the hidden layer based on your domain knowledge, measuring performance. If you realize that increasing more hidden layers doesn't give you more advantage, then I would suggest, stop there. That would be my guidance. But theoretically, I don't think there is any limit in terms of the number of hidden layers. If you have a GPU with a lot of CPUs in it, then I don't think there is any technical limit as such.
thank you, sir.
Sure.
You are talking about self-driving cars, but I have seen almost 3 years. It is in theory, but not in practical, or it is only in demo. So can you please explain what is that stopping to complete?
Yeah, if I understand your question, like you are talking about like the training cost and things like that, right? So
self-driving cars.
Yeah, correct. So that is the demo that I wanted to actually talk about. So let me give you like some basic intuitions for what that is, right? So let me see if I can give you a
my question is that it is in theory, because a lot of people are doing the self-driving algorithms, but it is not there in practical, or it is also in there only with the demo. Why so? For almost 3-4 Yes, it's over.
Yeah, so the thing is, like, to give you a specific practical example, like if you take a car like Tesla, then the advanced model has a feature called as autopilot, where you can say starting a destination, and it just like takes you there, right? And at this point in time, there are like some particular type of places where the algorithm has been like well tested, and that exists. So to your point, like it might not have come to different countries, but when I talk about the place where I'm living, that exists right now. I'm able to see that, and I have some of my friends who who have that self-driving cars, which is practical, right? And there are more than, what do I say, whether the technology is there, there are a lot of factors. For instance, the self-driving car, even though it has like got side mirrors, right? It is all cameras, right? But the regulation here says that it should look like a car and it should have some glass mirrors. But the glass mirrors don't do any job. But in a self-driving car like Tesla, what it actually requires is just a piece of camera, which is anyways there, right? So there are a lot of regulations which are kind of like slowing down the overall process of making the self-driving car possible. And at this point in time, it is already practical in the advanced model of some cars that I mentioned. And once the regulation and all other things kind of like get sorted out, then I believe like a lot of these things will become a lot more relevant and a lot more like distributed. But at this point in time, to your answer, to your question, self-driving cars exist as we speak today in the place where I'm living.
Okay, thanks.
Sure.
I think there's some question from Paris Gohan.
Sorry?
Came,
Are there any questions?
So I'm having one question, sir. There is some actually there is, what's the difference between multi-layer neural network and the deep neural network? That is, we can we apply this new deep learning concept for numerical data? Should we apply this only with images for feature extraction and all? And is it necessary to apply with numerical data?
Yeah, so from my understanding, like as I said, deep learning is something which is applicable across a wide variety of problems, whether it is structured data or unstructured data. It is like widely applicable. I have seen a lot of people by default use this for unstructured data because the other traditional approaches have no way to solve such kind of like problems. And when you take structured data, there are two cases, right? In one case, you want a lot of interpretation, wherein you wanted to understand, like if a customer is churning, why the customer is churning, right? So for that, you use some mathematical based machine learning models because the deep learning network, it doesn't tell you why something happens. The hidden layer is very black box, right? It just like learns on its own and you have no way to like interpret it very easily. So for those problems where you require less for that kind of problems, but for those problems where interpretation is the key, wherein if you are like approving a loan or not, and you wanted to tell when you're rejecting, why you are rejecting, for such problems, the application of deep learning is kind of becoming not very useful. That's because the regulation says you need to explain when you reject or approve a loan, why you need to do that. And deep learning at this point in time, it hasn't come to that very ready form where you can explain what really happens in all the hidden layers.
So thank you.
Hello, sir. This is Renosha. Hello.
Okay.
Hello.
Yeah, I'm able to.
Renosha?
Yeah, sir. No, sir. I want to say some feedbacks about this session, sir. Hello.
Okay.
Good afternoon, Excellencies. I thank God Almighty for giving me this opportunity to learn more about machine learning concepts, deep learning and reinforcement policies, that is learning ideas of policies, and the explanations were very clear, nice, simple, and easy to understand. And it's very helpful for me to take over my research into next level, sir. Thank you so much for your wonderful session, sir. And I request the organizers to arrange the sessions like this in futures also to enhance my research ideas. And thank you organizers for your great effort in organizing this international webinar. Thank you, sir. Thank you.
Osha, thank you. And
thank you, sir.
Is there any feedback from other participants? Just you can share your feedback now.
Hey, this is Christopher. Yes, feedback from my side. What an amazing speaker for all 3 days. Thanks for arranging the excellent session, Dr. Sozupra sir, Dr. Peter sir, Professor Ravi sir, Dr. Augusta madam, Dr. Sendil sir, and other organizers. Day 1, we cannot forget the Peter Augustine's big data research and tricks with Hadoop. All concepts are explained wonderfully, thoroughly. Day 2, Dr. A.S. Raja, what a resourceful person. Data science in the real world. Yes, he explained several real world examples like movies, mangoes, etc. So the real world example ignited the mind of many. I hope that the ignite will come with a good result. Through the session, Dr. Raja kept the audience at the end of the seat like climax in the movies. Thanks to Dr. Joseph Prasar for finding the gem in Dr. Raja. I think he might have find many gems, likewise our professor as well, the entire professor. Now we know more about Dr. Sir Joseph Prasar expertise. The day 3, Dr. A.S. Raja, today, I think he explained mind-blowing techniques, presentation, examples. What a wonderful session. Reinforcement learning with the deep neural networks. And also he explained with all the questions perfectly and given the constraints of regulation as well, the out of topic. He explained the concept like connected cars, churn, neural networks, image recognition, wonderful. Reinforcement using the game, ping pong, and self-driving cars, etc. Thanks for explaining, Dr. Raja sir. Newer technology and future engineering with the mind-blowing explanation and presentation. Thanks. Now our job is to extend this concept. I studied here this. I cannot live without this. I studied 20 years back. All the professor looked at my potential, saved me into diamonds in the market. Because of them, after studies, I lived and worked in my 15 more countries like USA, UK, Germany, etc. If I have a liberty to say during our college days, I won't forget. If next period is artificial intelligence, then we say. Then we say expert systems are is coming. It is none other than the expert, the HOD, Dr. Joseph Prasar. So what I'm trying to say here is HOD sir, Dr. Joseph Prasar, expert in AI 25 years back itself.
Thanks a lot, sir. Thank you.
And also I'll end up with the final words. The diamonds are made from golds formed from under pressure. So use this session to become diamonds. Finally, it is very useful and beneficial to all. We look for all those kinds of awareness. Once again, thanks to organizer. Thank you very much, madam. Over to you.
And this is my last portion, which I could not show earlier. But I will share in some material for explaining and giving you some pointers if you're interested in actually simulating and understanding the code which could go into developing your own self-driving car or simulating it. Thanks for that. Okay, over to you.
Are you sharing screen now?
No, I know like we have already like spent a lot of time. So I'm saying like I will share like more details over email.
Okay.
To this particular thing that I was talking about. But at a high level, basically what I was trying to say here is Amazon has a project called as Deep AR, where you can use reinforcement learning, and it's an international competition there you can participate. It's a reinforcement learning competition where they will give you, kind of like a random screen with some rules, and they will give you an actual car. So you have to like basically code, and there is a piece of button which when you press it will transfer the code from your machine to the actual car that they give it to you, and you can like put that car and it will like kind of like go around the track. But while you're developing the code, all you're trying to do is essentially develop a reinforcement learning algorithm, and you can change the rewards, you can change the policies, you can change the ideas that we have like discussed in the lecture, and you can come up with an algorithm, a reinforcement learning algorithm, and if it is powerful and if it beats the other competitors, then you are like given free tickets to attend their conferences and etc., right? So for particularly students who wanted to develop on reinforcement learning, this is a nice platform called as Deep AR, which exists. So it will help you to enhance your reinforcement learning algorithm, because it's a practical way to develop algorithms on top of a framework which already is available. You can use it as a basis to improve your knowledge on deep learning and develop self-learning cars.
Thank you, sir. Thank you for a valuable idea. Is there any other participants to say feedback, or shall we move on to the next session? Thank you, sir. Now I invite the head of the Department of Computer Science, Dr. V. Joseph Raj, to share a few words with us as a concluding remarks.
Good evening, everybody. Really, we enjoyed and learned the intelligent data analytics. I appreciate the effort of resource persons, Dr. Agustin, Dr. Raja, Dr. Saja, who gave the best performance on the topics big data research and analytics with the Hadoop, data science in the real world, and the reinforcement learning with the deep learning, respectively. I wonder Dr. Saja covered the topics from neural network to deep learning effectively. I feel and wonder these three experts are made for this international webinar on intelligent data analytics. The topic intelligent data analytics is the current trend and current need of the world. I mean, it may be industry or academic institutions or research. The research department of computer science of Kamaraj College is very happy and proud that we have been disseminating the new and needy concepts to the society world to the possible extent. I appreciate the participants who showed their interest to learn the new concepts. I wish you all the best. Thank you.
Thank you, sir. As a token of gratitude, on behalf of the Research Department of Computer Science, now I would like to express the vote of thanks. It may be lengthy, as I should thank everyone who are behind this 3 days webinar series. Please bear with me. First of all, I thank the Lord Almighty who showered his countless blessings to complete this webinar successfully. Next, I owe my gratitude to Thiru Ilango Vechivail, the president of Kamaraj College, who gave us a great platform to expose the insight on intelligent data analytics to the people with the spirit of learning. Also, I convey my sincere thanks to Thiru Rajendran, the secretary of Kamaraj College, and Dr. D. Nagarajan, the principal of Kamaraj College, for their motivation and constant encouragement to conduct this international webinar successfully. My deepest gratitude to our today's resource speaker, Dr. S. Saja, as well as the other 2 days resource speakers, Dr. D. Peter Augustine, Christ University, Bangalore, and Dr. H. Raja and Vasnan Kerala, for accepting our invitation wholeheartedly to share their applied knowledge to versatile participants in the field of computer science and for spending their precious time with us. I would like to convey my heartfelt thanks to our head of the department, the convener of this program, Dr. V. Joseph Raj, for his brilliant guidance and resources to complete this program in an efficient manner. Also, I extend my sincere thanks to my senior colleagues, the co-conveners of this webinar, Dr. V. Joseph Peter, Professor T. Ravi, and most importantly, one of the organizing secretary of this webinar, Dr. S. for their marvelous support and untireless efforts to conduct this webinar effectively. Also, I thank Mr. S.P. Ganeshan, Lab Assistant of Computer Science Department, for his technical support. Nowadays, technologies plays a vital role in conducting any webinars. In this occasion, I thank Mr. P. Saravanan, the Superintendent of Kamaraj College, who facilitated us with his team to conduct this webinar effectively without any technical flaws through Zoom app and YouTube live session. Also, I thank Mr. S. Praveen Zironmani, Research Scholar of Kamaraj College, for his wonderful technical assistance for e-communication. Finally, I wholeheartedly thank our young-minded participants with more spirit of learning who have participated from various academic institutions and industries by allocating the time to attend this webinar series in the midst of their busy schedule to make this program a more successful one. Once again, I thank you one and all. Thank you.
Thank you very much.
You can find today's feedback in the form in the chat box, and please submit your feedback. And you can also find this webinar series in YouTube link. We'll pass the YouTube link with you. You can refer the YouTube videos for your future reference. Thank you. Stay home, stay safe, and happy learning. Thank you. Thank you and all.
Thank you, Sajjan.
Thank you, sir.
Thank you, sir.
Thank you. Thank you.
I think Paresh, Joel, Malay, and many were there. They tried to ask questions, I think, on that question session.